I was just watching Sabine's talking about the principle of least action, and you often see a diagram like this in physics books. Well, usually they're better than this because I didn't draw straight lines, but these are supposed to be two straight lines with a kink in the corner here. That's supposed to be straight, and that's supposed to be straight. And you say, what is the path that the light takes from A to B when it's moving from air to water? And who was it? Bernoulli? Bernoulli said it goes in a straight line, and then Fermat said that it takes the path of least time. And then the mystery is how the light knows. But and I looked up Huygens' principle in this book by Grant and Phillips, but it doesn't mention it. And listening to Vandana Shiva talking about David Bohm, I remembered being struck by David Bohm's comment in, I think it must have been Wholeness in the Implicate Order, where he says, or is it causality and chance in modern physics? Is that David Bohm's book, or is that Feynman? Bohm wrote a book about causality. I think maybe the title of that was just Causality. I should have looked it up. He mentions Huygens' principle as being a way to find out what this works. And Huygens' principle, there's a very good Khan Academy video by Mahesh Shenoy, where he explains how Huygens' principle can show you how you get diffraction from a wavefront passing through a slit, and the principle is that the space is full of, the medium is full of little oscillators which excite each other. So when you have a point here with a light bulb, you get some excitation, and now you'll get a wave front moving out, but he starts actually right at the point, but if we draw the light bulb there, I need my glasses for this, can't see anything. We have each point on the surface of that bulb is a point where a light ray is coming out. And instead of talking about light rays, which are like photon paths, they're a bit difficult to think about, Huygens says, well, each of these is the source of a new wavefront. So we have a tiny little circular wavefront around each, but these are actually around each point on the surface of the bulb. I'm only drawing them barely touching, but in fact they're overlapping all the way around here. And the places where they reinforce each other are along the common tangent. So the new wavefront is like that. And then all the way along that new wavefront, there are these little wavefronts. I'm drawing this far too small. And so you then get another wavefront. And the rays are always perpendicular to the wavefront. So if we draw this a bit bigger, say that's the surface of the light bulb, then all the way along here there are rays, and it's something like this. And you can kind of see that for every point inside this loop, there's some kind of cancelling out by other loops, other neighboring loops. But along here, there's nothing but reinforcement. But you don't need to think about a particular wavelength. We're just talking about a particular time interval, however, whatever is the speed of wave propagation. But you could choose your intervals to be a wavelength, and then these would be the peaks. That would be the peak or the trough, or it could be the central point if your wave was a sine wave like that. You could say that this is the surface of the bulb. And then you would draw these would be half waves, so you would draw your circles to be one wavelength. And there would be one wavelength along the next one, which would be that point there. And you can kind of see that, well, in this case, they're going to sum to zero all the way along the wavefront around there, and they're going to sum to zero all the way along here, and they're going to reinforce, so you're going to get the peak of the wave is going to be there and there, if that's the surface of the light bulb or the light source. So when you go to this picture and you see the physicist leaves out the source and leaves out and says, how does light know to go from point A to point B? Well, Sabine did this in particular, and that immediately rubs out the boundary conditions. It makes the problem actually seem much more complex, because you think these are two arbitrary points, but no, this is actually a point with some sort of detector. It's got some sort of photosensor, and this is a point with some sort of source. And I can't remember his name, the neuroscientist, Karl, it's not Frisch. Anyway, talking about inactive cognition. I was thinking about this when I got to Bolivia, and I wrote to Karen, who was my first girlfriend. I wrote her. I was writing her letters and things, and in particular because she had a squint from childhood. I guess from birth, she'd had one eye was slightly squinted, and she said for some reason she decided to get it corrected, and she'd had some laser surgery or something, and they'd done something to one of the muscles, or And she said she was having a terrible time because she couldn't, she was losing her balance and feeling dizzy, and all sorts of terrible things were happening. And I said, oh, I've been thinking about this whole business of embodied or inactive cognition. And now that you say this, it's kind of obvious that what the cause is, because I always used to say to her, that she according to theory didn't have three-dimensional vision, because only one of her eyes was looking at the place, and the school book physics that we learned said that the way we see in 3 dimensions is by getting a simultaneous image from both eyes, and because the eyes are apart, they each see a slightly different image, and it's only because they're both looking at the same object and are able by kind of parallax to infer the distance. But the reality is that if you don't have that, there are other ways. You know, the movement of your head and the movement of your eyes. One eye will, both eyes worked fine. It's just the one didn't point the same direction. So but if she covered up one eye, she would see out of the other. If she covered that eye, she would see out of that. So there are all sorts of ways that her brain could have adjusted to perceiving depth by movement or by alternating or something. And then when her brain basically would have learnt how to see in 3D through her body. And then they changed her body, and then her brain couldn't see in 3 dimensions, and wouldn't have been able to. And I haven't spoken to her since about it. I don't know what happened. But anyway, I wrote to her about it, and I said I'd been thinking about cognition, and I couldn't think of any examples of any animal's behavior where there wasn't some sort of action involved in cognition. And Karl Fitch is talking about how it's with respect to the potential that that we perceive. So we perceive objects because of the potential for our action to reach out and pick them up. So this is a kind of learning development in children, that a baby, because the baby doesn't yet control his or her hands very well, actually learns to distinguish different objects by their potential for being grasped. And you can see how a kind of reinforcement learning can arise in that kind of situation. So as you're learning to move your body and move your arms, you're also learning what are the objects in your world that you can grasp or touch. And you can kind of see in this principle of free energy is I didn't quite understand the mathematical. The free energy is the variation principle of not least surprisal. It's something is a variation principle of some maximum. I haven't even read the page, the description of what this thing is yet. But I did think a lot about it in Bolivia. I was thinking about probability as well and cognition. Anyway, so back to Huygens. I'm very tired. I'm not making a very good job of this. When you have a point B here, the light is not just going from A to B. We don't actually, we don't know that. What we mean is that we have put something here, an eye, for example, the eye of a fish, and that is, a fisherman, or that's a fish, and that's a fisherman's eye, and the fisherman is looking for the fish. So there are systems at either end of this. This is a whole system. So if you want to understand how light behaves in here, you're interested in the point B in particular, and the only light from A that's going to arrive at the point B, or vice versa, if that's the fish and it's going to there, the only light reflected off the fish that is going to reach the fisherman's eye is the light that goes that way. And Huygens principle will derive that. Or much more complicated, you can do Feynman, and you can say, well, photons have these tiny little spinning clocks on them, and the arrow spins as the photon moves, and then we sum up all the arrows depending on the path length and the number of times the arrows have looped. But he's really just using another language. He's talking about these rays, and he's talking about the spinning as being some complex, some point on a unit circle in the complex plane. But that's really only a linguistic thing that, and he wants to talk about that because he doesn't want to talk about a medium, because he's talking about light passing through a vacuum, and we don't know what's in that vacuum to actually have these effects. It can't be an electromagnetic field, because we're talking about the gauge bosons of the electromagnetic field theory in Feynman's language. We're explaining the field. We can't use it, so we have to explain it in terms of something else. And this is a state vector in a Hilbert space. But as Vandana Shiva points out, it's always in a phase space. It's always a whole lot of state vectors together. Talking about the state of a single photon is not a particularly useful way to look at the thing, because it's the phase space of all the photons that are in this whole soup here. It's not that one photon was emitted from here and we're tracking it. We're looking at the interactions of all the photons everywhere. And that's something you kind of lose in when you're following the details of how these spinning arrow pictures add up. And it's what you lose when you talk about a photon as a quantum system. A quantum system is never a photon. It's the whole apparatus. It's the potential for the receiver to receive, and it's the potential for the transmitter to emit, and those are the boundary conditions, and then the system is definitely the whole thing. That's how you have to think about it. But there's so much of this point A to point B type explanation going around, and it's the same in Veritasium's video. He starts out talking about points A and point B, but then he does start talking about boundary conditions later on. But I think it would be much clearer if you started out saying that we have to have a physical setup. An experiment is an arrangement of macroscopic laboratory apparatus which which we set up, and then we, with a particular view to demonstrating some kind of effect like refraction or reflection or diffraction or and then we need to be able to describe these effects as kind of universals, and then this principle of free energy gives you a statistical handle on it. It gives you a way to describe it statistically. So it looks really interesting, and I think that would be a better way to kind of teach physics, from the point of view of whole systems, not from the point of view of presenting puzzles to students like, what does the photon do? And it's very unsatisfying as a student to have it drummed into you that light is not a wave, it's a particle, and therefore it's incomprehensible. It's not helpful. It's definitely not helpful. But Khan Academy's video on Huygens' principle is a nice start. So that's it. I'm dropping off. I'm falling asleep. This was a very strong cup of tea, but I'm still tired.